Hello, welcome back to the lecture of thermodynamic properties of ideal Fermi gas. So we have already discussed the limiting cases when n lambda cube divided by g is very much less than 1. That means temperature is very high. Temperature is high. Okay, so this is corresponds to the classical case. So this Fermi gas behaves as a classical gas, classical ideal gas. Then we have also discussed n lambda cube divided by g is very much tends to infinity. That means approximately tends to 0. So this also we have discussed in the last class. So this is called ground state. Okay, ground state. And T is equal to 0, that is called, the temperature is 0 means 0 Kelvin is called ground state. Okay, so T is equal to 0 Kelvin. So we have discussed this case also. Now we have to go for the case when n lambda cube is very much greater than 1, but it is finite. Okay, that means T is not 0, C is greater than 0. That means T is finite, low temperature. Okay, so low temperature case. So today we will be discussing this. Okay, before going to the thermodynamics of the system at low temperature, we can see the mean occupation number of the Fermi system at low temperature. Okay, so we know that at T equal to 0 Kelvin, so the average occupation number or mean occupation number is a step function. So we have plotted this thing in the last class. So we, in this axis energy corresponding mean occupation number in this axis. So if we increase the energy, so here this is mu 0, and we have this mean occupation number is given by the relation 1 divided by e raised to t minus mu by kt plus 1. Okay, so this value is equal to 1 when e less than mu 0. So this is a graph. So this is 1. And if it is greater than mu 0, if the energy is greater than mu 0, this value will become 0. Okay, so this is the graph. So this is at t equal to 0 Kelvin. Okay, now let us see that temperature is very small but not 0 Kelvin. So in that case, so the mean occupation number graph will be, okay, so it will be like this. Okay, so the graph deviates from this ground state graph, but not much deviation is there. Okay, so in the deviation of the mean occupation number at low temperature is very small deviation. But at low temperature, that is the temperature smaller than the characteristic temperature mu 0 by k. If the temperature is smaller than this value, then the deviation from the case when t equal to 0 is significant only when energy for which the E minus mu by kt, E minus mu divided by kt in this expression is of the order of unity. That means it is approximately equal to 1. In that value only there is much change from the t is equal to 0 graph. So otherwise this value, this graph coincides with the t is equal to 0 graph here and here also. So therefore we can write the thermal excitation of the particles in the Fermi system occur at a very narrow range of energy. Okay, so only at this energy around this mu 0 only thermal excitation happens. So a narrow range of energy around it, E equal to mu 0, and has a width of this has a width of kt. So this width So this width is kt, of the order of kt. Now the fraction of particles thermally excited is therefore the fraction of particles thermally excited. So what we are getting it? See, we know that at T equal to 0 Kelvin, T equal to 0 Kelvin, entire energy levels are occupied with 1 particles. Okay, that means an average number of particles per level is 1. Okay, now when temperature is slightly increased, so this value, this energy is called EF. Around this energy, excitation happens. That means near to this EF, excitation of the particle happens. All other particles remains unaffected, or the internal energy levels are unaffected. Okay, so only these particles are excited. So thermal excitation, the fraction of particles thermally excited is given by fraction equal to of the order of, what is that, kT by EF. Okay, അപ്പോൾ ഇത്രയും നമ്പർ ഓഫ് പാർട്ടിക്കിൾസിന്റെ ഇടയിൽ എത്ര ഫ്രാക്ഷൻ ആണ് ഇതിൽ നിന്നാവുന്നത്? KT by EF fraction മാത്രമേ എക്സൈറ്റഡ് ആവുന്നുള്ളൂ. Okay. So the bulk of the system remains unaffected. Okay, by the rising temperature from 0 to 0 K. The thermal energy per excited particle then is therefore, for an excited particle, the thermal energy is equal to, is of the order of K into T. Thermal energy, you know, if T is the temperature, and for one particle the temperature is T, then KT is the thermal energy. So now initially it was, let us assume that it is at T equal to 0 Kelvin. So only the thermally excited particle has energy KT. Okay. Therefore the total number of excited particle. So we can raise, we can thermal energy of the system. The system, or the thermal energy of the total excited particles is equal to, so of the total particle only this much fraction is excited, therefore n times kT by EF is the total number of particle excited, and each particle has energy kT. So this is the thermal energy of the system. Okay, excited thermal energy of the system. So this is of the order of, you can say only, it's not exactly that value, is of the order of n kT EF, kT by EF into kT. Okay, so we can write that this is equal to, this is of the order of, okay, so therefore the specific heat of the specific heat CV is equal to, so this is the, so specific heat is, specific heat, we can say that specific heat is proportional to temperature. For at low temperature the specific heat is directly proportional to the temperature. Okay. Now let us see the thermodynamic behavior of the system at low temperature. So the here the function can be expressed as asymptotic expansion powers of log z raised to -1. Okay. You see the appendix in the Patria textbook, appendix E. Okay. So this is by using Sommerfeld's lemma. So therefore we can write f nu of z is equal to, there will be log z raised to -1 whole raised to 4 terms also. So to the first approximation we can put it like this. So this is the value of Fermi Dirac function f nu of z in terms of the powers of log z raised to -1. We have been using f5 by 2 of z, f3 by 2 of z, and f1 by 2 of z in our many formulae used in the thermodynamic quantities. Okay, so we can write f5 by 2 of z is equal to, using this thing. So here, similarly, f3 by 2 of z also can be written as, similarly, f1 by 2 of z is equal to. So using this Fermi-Dirac functions, we can write the equation for pressure, temperature, sorry, internal energy, specific heat, Gibbs free energy, sorry, Helmholtz free energy, and entropy as well. So therefore, we can write for using this f3 by 2. So we know that the n by v, the equation for n by v is equal to g by lambda cube f3 by 2 of z, where lambda cube is equal to, and substituting this value of f3 by 2, we'll get, so this is n, and n is equal to g 2 pi m k t whole raised to 3 divided by 2 h cube into f3 by 2, 4 divided by 3 root pi log z raised to 3 divided by 2, 1 plus pi square by 8 log z raised to minus 2. Therefore, we can write kt log z whole raised to, so therefore we can write kt log z is equal to. So to the first approximation, we have neglected all of the other higher order terms. We can write in the first approximation, kt log z is equal to the zeroth approximation. You can say that kt log z is equal to. Then this term will be neglected in the zeroth approximation. So, okay. So this is nothing but this is the equation for Fermi energy. So in the next approximation, we can say, we can write, that is using the expression. Okay, so in the second approximation, we can write like this. So kt log z, what happens to kt log z? Therefore, from this kt log z is equal to whole raised to minus 2 by 3. So this goes that side. Okay, so it will become 10 whole raised to minus 1, then raised to 2 by 3. So it will be whole raised to minus 2 by 3. So this is equal to, so n by 4 pi for pi g raised to 2 by 3, a square by 2m is the value of ef. So this is approximately equal to this value. We can write mu. This is mu is equal to ef into 1 using the Taylor expansion. So this will become minus pi square by 12. It become log z. Log z is equal to kt equal to 0. So we can write that pi square by 12 by 12 is equal to temperature is not equal to 0 at T. Temperature is low, mu is equal to mu. Okay, or we can write this as ef of t is equal to, or we can write ef of t is equal to f at 0, okay, into 1 minus pi square by 12 kt by ef whole square. So this is the relation between ef of t and ef of 0. Now next is we wanted to find out the internal energy. Internal energy is equal to the energy of the system is equal to 3 by 2 3 by 2 nkt f 5 by 2 divided by f 3 by 2. So if we substitute the asymptotic expansion of f5 by 2 in terms of log z raised to minus 1, then we will get this thing, this value as, so f5 by 2 f 3 by 2, this will become 5 log z. You can see that 2 by 5 log z is equal to 3 divided by 5 nkt log z. We wanted to put in the first approximation, so we'll get 1. So here this is pi square by 8 all raised to minus 1. So this will be 1 minus pi square by 8. So this is, so minus pi square by 8. Here 5 by 8 pi square. So it will be 4 by 8 pi square. So we can write 1 plus 4 by 8 pi square log z raised to minus 2, etc. Okay. Kt log z is equal to the chemical potential, which is equal to ef into 1 minus pi square by 12 kt by ef whole square. So substituting this value there, the other in the equation, the average energy per particle is equal to 3 divided by 5 ef 1 minus pi square by into 1 plus pi square by 2. Okay. So to the first approximation, we can neglect the higher order terms. We can just take this kt by ef whole square term only. The other terms, we can higher order terms we can neglect. The is equal to 3 by 5 ef plus 5 pi square by 12 kt by f. Okay. So the internal average energy. So this can be written as E bar. E average. The average energy per particle of the system increases as the temperature increases from 0 Kelvin. And we already know the Fermi energy at a lower temperature, that is other than 0 Kelvin, that is EF is equal to EF into 1 minus 1 minus pi square by 12 kT by EF whole square. So from these two equations, it's clear that the average energy increases as the temperature increases, but the Fermi energy decreases as the temperature increases. So we can physically explain using this diagram. Okay, so there are many energy levels. So this topmost energy level is called as EF at a T equal to 0 Kelvin. Okay, now at a T equal to 0 Kelvin, all the systems, all the states are occupied with a particle. So that's why this is called Fermi energy. Okay. Now, when temperature greater than 0 Kelvin, what happens? The topmost energy levels, the particles with the topmost energy are thermally excited to higher energy levels. Okay. So this particle goes to higher energy levels. So what happens? Their energy increases. Therefore, the average energy slightly increases as the temperature increases. So this is due to this plus sign, it is increasing. Now what happens to the Fermi level? Now this particle has escaped from these two. That means it has gone to the higher energies level. So this Fermi energy level decreases. Now up to this, there are particles occupied, completely occupied. So this is new Fermi energy level. So Fermi energy level decreases as the particle thermally excited. So that is the meaning of these two expressions, Fermi energy and average energy per particle. Okay. Now the pressure. Let's see the pressure. Pressure of Fermi gas at low temperature. Pressure of Fermi gases P is equal to 2/3 of energy density. Okay. So which is given by 2 divided by 3 of U. We know U by N. So U equal to 3 divided by 5 N EF into 1 plus 5 by 12 pi square KT by EF whole square. Okay. So divided by P is there. So this is U, then divided by P. So this is the pressure of the gas as the temperature increases from 0 Kelvin to a finite temperature. Okay. So we have discussed number density, energy, average energy, and the chemical potential, sorry, mu. So which is called EF. Next is the specific heat capacity. So we have U is equal to 3 by 5 N EF 1 plus pi 5 pi square by 12 T by F whole square. Okay. Specific heat at low temperature is equal to dou by dou T of the internal energy at a constant number of particles and volume V. So we can write So finally what we are getting is, so pi square by 2 nk into kT by EF. This is the specific heat of the Fermi gas at low temperature. So here this, what is this fraction? This fraction represents kT by EF is the, or the fraction of particles thermally excited, okay, as the temperature increases. So we have said already that അതായത് നമ്മൾ പറഞ്ഞു temperature 0 Kelvin നിന്ന് കുറച്ച് കൂട്ടി കഴിഞ്ഞാൽ only a small fraction of the particles are excited. എവിടെയാണ് എനർജി മ്യൂ സീറോ എനർജി, അതായത് ഫെർമി എനർജിന്റെ അടുത്തുള്ള അറൌണ്ട് ഫെർമി എനർജി ഉള്ള പാർട്ടിക്കിൾസ് മാത്രമേ എക്സൈറ്റഡ് ആവുള്ളൂ. ഓക്കെ, അത് വളരെ ചെറിയൊരു ഫ്രാക്ഷനാണ് കെ ടി ബൈ ഇ എഫ്. ഓക്കെ, അത്രയും ഫ്രാക്ഷനെ കൂടും. അതുകൊണ്ട് ദാറ്റ് ഓൺലി കോൺട്രിബ്യൂട്ട് ടു ദ സ്പെസിഫിക് ഹീറ്റ്. ഓക്കെ, the Fermi energy EF can be expressed as K times TF, where TF is the Fermi energy. So if the temperature of the system, Fermi system, is very much less than TF, that means this KT is very much less than EF. So then only we can use this expression. Otherwise, there will be higher order terms come in this expression of CV, internal energy, and pressure and all. So if temperature is very much less than Fermi temperature, then the specific heat of the gas is, Fermi gas, is directly proportional to the temperature. We can draw the graph of specific heat versus, so CV by Nk, but CV by Nk and T. So we know that at high temperature, the specific heat is, the value of specific heat is 3 by 2. Yes, specific 3 by 2 Nk. So this is at a high temperature. So as the temperature, so from the asymptotic expression of the specific heat, we have seen that the specific heat of the gas decreases monotonically, and at a high temperature the specific heat is 3 by 20, and at 0 temperature the specific heat of the gas is 0. And from this expression, that means we have neglected the higher order terms, so we can write that this is directly proportional to temperature. So we can draw the graph like this. Okay, so at low temperature this is proportional to T, so CV is proportional to, so at low temperature CV is proportional to T. Okay, so this happens in metals also. So the electron, so metals can be considered as a free electron gas. Electron specific heat of the metals is proportional to T. Now next is we wanted to see what is the Helmholtz free energy. The Helmholtz free energy, the Helmholtz free energy A is equal to N mu minus PV, G minus PV. Okay, the Gibbs free energy minus PV. We know that mu is equal to, and also we have P is equal to, okay, so applying this to in the above equation, so we can write A is equal to, okay, so this is to the first approximation. If we have higher order terms, it will be we have more terms in this.
The next is the entropy. Entropy of the system at a finite temperature, finite low temperature. That means S is equal to U minus A divided by T. So therefore we can write S divided by Nk is equal to pi square divided by 2 Kt divided by F. Okay, if there are higher order terms we can write like this. So S by Nk is equal to pi square by 2 Kt by Ef is the entropy at a very low temperature, which is the temperature is very much less than Tf. So the entropy of the system is directly proportional to the temperature at low temperature. Okay, so when T is equal to 0 Kelvin, S is equal to 0. Okay, so we have derived all the thermodynamics of the ideal Fermi gas. So that's for today.